Okay, now welcome back. So we'll pick up where we left off. We actually got ourselves to this point where we factorize out the temperature differences. Inside here we will have a collection of y's over here. We have y's over here, y over delta p, y cube over delta p cube, 1 minus blah 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 blah. Okay, so how do we get around to do this? Okay, so yeah, good question. Okay, so we'll need to think of a smart strategy to go around dealing with this. Okay, so we notice that here it's a product. You look at this. This is a product of two things. We can actually multiply everything out, which I frankly am not looking forward to. The other way is to integrate by parts, which I think is a slightly wiser solution. Okay, of course we can use Wolfram as well, but the thing is that now we have two types of boundary layers to deal with. Okay, we have two kinds of boundary layers to deal with. So I'm suggesting an integral by parts should work the best, because one part has to deal with the delta p boundary layer, one side has to deal with the delta t boundary layer. Okay, so let's do that to make life easier. Let's evaluate the integral. Alright, so this is a bit of a challenge, but we'll try to get it done. Okay, so that's one. So what do we do when we integrate things by part? Okay, you know what, on second thought, maybe integrating by parts is not the best idea, because the moment we do that, okay, the moment we integrate by parts, one of the sides will you will have to differentiate one of the sides, and then you still have to have a messy integral to multiply into anyhow. So that may not be the best idea. Okay, so I will take inspiration from some Google search, and again I paste this PDF here for your reference. So basically what they do is to integrate by substitution. Okay, it's from NPTEL, NPTEL. It's from India, one of the lectures you can go and download. Basically they do integration by substitution, and what we do is this. Okay, let's substitute dy, the integral with substitute the integral for dy with y over delta t. Not difficult, yeah, not difficult. Okay, so how then do you do this? Okay, how then do you do this? So we can put dy equals to delta t d, fraction y over delta t, because delta t here is constant with respect to y, and delta p as well. Okay, note delta t and delta p, both boundary layers are constant with respect to y. When you fix x, because this is delta t and delta p are only functions of x, and we're not dealing with x here, so it doesn't really matter. So let's just substitute this into our equation. Okay, subs the change of variable. Okay, so it should be a lot better. Okay, dy over delta t will be at the back. Then of course delta t we can actually just bring it all the way out to the front. Okay, maybe I'll put it at the back first. Okay. And I'll paste the integral here just for clarity. And let's do it. Okay, so now let's bring the integral, the delta t out. Of course, now also we have to change limits. So instead of going from 0 to delta t, it will actually go from 0 to 1. Because when y equals to delta t, y over delta t will just equal to 1. Okay. So not too bad. However, it still looks very messy, okay? Let's do this. Let's replace okay, let's give it some random, okay, maybe I'll use beta. Give it some random Greek letter. That's usually the drill, isn't it? Let's substitute beta equals to y over delta t. Okay, it's not really material what letter you use. Okay, so long that as is the correct letter, is the same as so long as your nomenclature is consistent throughout. So let's put beta wherever you find y over delta t. Okay, beta. And last but not least, you should have a d beta as well. Okay, so I've replaced it 3 times. Okay, it's very good. I think I can take the brackets off the beta. And this looks like a much more palatable integral to deal with. Of course, if you want, we can just get rid of the minus sign here and plus do a little plus minus thing here. So we get rid of the minus sign. Yeah, we get rid of the minus sign to obtain the following. Okay, so if beta equals y over delta t, this also means that y equals to beta delta t. Okay, so let's substitute y equals beta delta t in there in the next bit. Okay, y equals to beta delta t. So let's substitute beta delta t all throughout. Okay, so then you will have a very rough simplified integral. Okay. Okay, very good. Okay, so now we have this, we can actually separate out some integrals for ourselves. Okay, we can actually separate out some of these integrals. So we separate this out into 2 integrals, okay? Once there are 2 terms here with this delta t over delta p. So these are the boundary layer ratios, which I guess we can leave it as such. So I'm going to have 2 integrals here. So we'll multiply this bracketed term, this whole bracketed term here, into both of these integrals, both of these places. Okay. And of course, I'm expecting it to run off the page again. Okay, I'm expecting it to run off the page. Okay, so Now we have this, let's separate out these two integrals so that we make life easier for ourselves. Okay. So we'll have this integral applied, this delta t integrate from 0 to 1. Okay, so I'll have a d beta here, d beta. Now I'll just copy and paste all of this over here. Okay, nothing too bad about it, I think. Alright, so now we have this. We can factorize out this delta t over delta p cubed and delta t over delta p over here. Okay, so we'll just do that. So let's have a fraction in front. So beta I can take out of this one, and I'll take the fraction to the front because it is not dependent on y at all, this ratio. Delta p and delta t are both independent of y, so that's why I can do this. Okay, so again I'll bring beta out here, and I'll bring this cube to the front so we don't have to deal with it in the integral. Okay, so now this is a form we can start to kind of use in Wolfram. Okay, so I'm just going to multiply all of this in so that we can start plugging in the numbers into Wolfram. Okay, so beta here will be I'll paste it here, then beta will become beta square here, and then this will be beta to the 4th power over here. Likewise here will be the same thing, right? So let's find that beta. Okay, the beta, I'll take it out, I'll cut it, and then I'll paste it here. The beta here becomes beta squared, beta cubed becomes beta to the 4th. Alright, so these two integrals, well, let me factorize out the 3.5 and the half. Then we'll start doing Wolfram. Okay, let's factorize out the 3.5 and this other half out of the integral. Okay. Fraction 1 over 2. Integrate from 0 to 1. Okay, I'll bring the fraction 1 over 2 here. Let's see whether I did the math right. So bring the 3 over 2 out. Okay, I think there's an extra little bracket here. Yeah, there are a few extra brackets. Okay, yeah, I think since I multiplied it out, there was extra brackets. Okay, so okay, let me clean out the brackets first. Okay, so you see I've cleared out all the brackets. 1, 2, 3, 4, 5, 6. All of these brackets are now cleared out. Of course, this 3 over 2, let me bring it to the front just for the sake of neatness. Presentation, you know, it's important. Let's now look for Wolfram. Okay, this is the reference I got it from, so later you can check it out. Now I'll just do it live in front of you. Wolfram. Okay, so let's do the first integral. Actually, the first and second are almost like identical since I actually already factorized out the half and the 3 over 2. It's not too much of an issue. So integrate from 0 to 1. So those are our limits. So this beta I will just replace with x minus 3 over 2 x squared. X minus 3 over 2 x squared plus half x to the 4th dx. Now let Wolfram do the job for us, and then we should be able to get similar numbers for both. In fact, this thing can be sort of factorized out, this integral. Okay. All right. Oh, okay. Let me get this. Okay. Unfortunately for us, this integral actually reduces to something very simple. Integrate from 0 to 1, you just get 0.1 here. Alright. I hope that is right. If there's any careless mistake, just let me know. 0.1, which we can go to the front, or maybe you just divide the front by 10. Divide the front here by 10. Alright. Now we are talking. We are sort of in business. Okay. Okay. Okay, so I think that's it for now. Yeah, I'm going to take a break after this, so I'm going to substitute this back and then I'll call it a day. I'm going to drink some water or something, you know. Okay. So you can substitute the integral back. Okay, substituting the integral back, we will just get this. Where's the integral? Okay, so that's where I will leave things. If there are any careless mistakes, again, please let me know in the comments. So it's for everybody's benefit, you know. Okay, so thanks for watching. I'll see you guys again in the next video. Goodbye.